Hello, guys. Welcome back to MedZone African Motives. Still working on our Electrotechnics N4, that is working on the EMF equation, which is of a DC machine. So I just want us to go through typical questions that you might be given working with the EMF equation of a DC machine. So it is something that is important in your calculations that you are going to need pertaining the EMF equation. All right, so for our direct current machines, we are already given the formula that we are going to use when calculating this E, which is the generated EMF can be given by this formula, that is 2 times Z times N times P times flux, which is over 60C. So this is just the number of conductors. So we are considering the Z there, which is the total number of armature conductors. So that is the total number of armature conductors. So we are talking about the total number of armature conductors. So you'll be given direct these number of conductors, or sometimes you are given as the slots and then give a number of conductors per each slot, where you just need to multiply the number of the slots to the number of conductors per each slot that you're given. All right, then you're also having the N. So when you're having the capital letter N like this, there is a presentation that the speed is in revolutions per minute. So this N is the speed that is in revs per second. All right, so that is our speed. In this case, we are referring to the speed in revolutions per minute. That's why we've got the 60 that is dividing them. So if I use a small letter n, it means I'm not going to use this 60 because this small letter n is in revs per second. So dividing by 60 there, it is a conversion to the revs per second. All right, then we have got the P, which is the pair poles. All right, so these are pair poles, the number of pair poles. If you're given the number of poles, then the pairs, just like the poles divided by 2. That is, in this case, we are simply talking about the number of poles divided by 2, which is the number of poles divided by 2. So whatever that you're given, because remember, a pair, you're talking about two things that are representing the same thing. So to obtain that pair is what you're given divided by 2. That is the one that you're representing as your P. Then we have got the flux, which is the useful flux. So there we are talking about the useful flux that we are given, and it is taken per pole. So this is taken per pole. Remember, the units for flux is Webers. All right, then C, representing the number of parallel paths. So this C is actually about the number of parallel paths that you are given. So it is going to affect that it is either a wave wound or it is a lap wound. So these are the two things that will affect our C. So on a condition that you are working with a wave, you are going to use the C being equal to 2. Then for a lap, your C is equal to 2P. That is the conditions that you're going to have. So meaning to say, this C that you are having, it is going to be affected with the conditions that you're given. Is it a wave or it is a lap? Remember, P is representing the pair poles. These are pairs, not the number of poles, but the pairs that you are given, the pairs that you are given. Those are the ones that you are using on this part, okay? So that means if you multiply, it is going to be 2 times the pair poles. It is simply the number of poles that you're given. So for a lap, it simply means your C is equal to the number of poles, okay? But if you're given a wave, your C is going to be equal to 2. That is the condition that you are given. So like I said, the Z also can be affected on a condition that maybe here you are given the slots and the number of conductors. So it means in that case, you are going to multiply the slots times the number of conductors that you are given per watt per slot. So it depends with the condition that you'll be given in order for you to obtain that Z. But these are the conditions that you will need in determining of this given EMF. Then the other thing that you're going to need there, maybe you might be given two conditions of a DC machine, the same DC machine, but given different conditions, maybe when the EMF has changed or when the speed has changed. It follows that the EMF is actually directly proportional to the flux and the speed. So meaning to say E is equal to the constant times the, remember, guys, from your proportionality, if you're given a proportion, you remove that proportion with a constant. So the K that we are seeing is a constant, but E is proportional to the speed times the flux. So with this condition, it follows that when you are given the first condition of a DC machine, and you're asked the conditions of the second part. With this part, it follows that E1 over E2 is equal to K, N1, then we're going to have flux 1, then we're going to have K, N2, flux 2. But remember, the constant there is the same. And given the same machine, that means you might be given a condition that the speed is the same or the flux is the same, depending with the conditions that you're given, or maybe the speed has changed, the flux remaining the same. You can calculate whatever that you're given. You can even calculate the generated EMF at the second condition where you are given the effect in terms of the speed. So the speed can remain the same. It can change, same as the flux. It can remain the same or it can change. So that is the conditions that you might be given. So with the conditions that you're given, those are the ones that you use now to answer your question. So with this, you can answer any typical question actually on a DC machine talking about the EMF equation. So these are the typical questions that you're given. If we are to consider first part of our question, we are given that there is a 6-pole, take note, a 6-pole. These are the number of poles that you're given. 6-pole, the number of poles. But on the formula, we are not using the number of poles. We are using the pair poles, which is the number of poles divided by 2. So from the number of poles that you're given, P, which is the pair poles, is going to be 6. The number of poles divided by 2. So that will be 3 pairs. So meaning to say, in terms of the pairs, we're talking about 3 pairs. It's a lap wound armature. A lap, it affects the C, which is the number of the parallel part. Remember, we say for lap, the C is equal to 2P, which is effect. If it was a wave, it was going to be 2. But in this case, it's a lap. So C is equal to 2P, which is simply 2 times P. Remember, our pair poles, they are 3. So meaning to say we have got C, which is 6. That is the condition. How many conductors that we are given? 360 conductors. So we are given the Z, the number of conductors, 360 conductors, and is driven at a speed which is in revolutions per minute. So this is our capital letter N, 1,500 revolutions per minute, which is revs per minute. Calculate the EMF generated when the flux per pole. So the flux is taken per pole. So our useful flux per pole is taken as 40 milliwebers. So calculate the generated EMF. So from the formula that we are given, we saw that the generated EMF, we can calculate that from the product, that is 2 times the useful flux, the number, which is the speed, the number of pair poles, the number of conductors, then over 60C. So you can substitute in this formula to determine the generated EMF. The EMF generated. So that is 2 times the flux, useful flux, that is 40 milliwebers. So remember, milli, that is times 10 to the exponent of -3. The speed is in revolutions per minute. That's why we are using our formula with a 60. So that's 1,500 times P, the pair poles. How many pairs are we having? That is 3. Then we are given the Z, the number of conductors, 360. All right, so this is going to be over 60 times C, which is our C. Remember, that's a 6 for a lap. So meaning to say, if it was a wave, this C was going to be affected. The C was going to be equal to 2 if it was a wave wound. But in this case, this is a lap wound. So that is the idea. So with this, we are going to obtain the E, which is the generated EMF, and that was going to be 360 volts. Remember, this is the voltage that you are working with. So just like that. So this is how you're going to be given these typical questions. Question number 2, you're given an 8-pole. So just like the previous case, what is it? The number of poles. There are 8. So meaning to say the pairs, 8 divided by 2. We are now talking about the pairs. So we're giving 4 pairs. An armature is wave wound. So for a wave, it gives us the value of C, where C is equal to 2 for a wave. So there we are given, and it has got 118 conductors. So we are given already the number of conductors, 118. It generates an EMF. So we are given the EMF that is generated, which is 400 volts. Determine the speed at which it is running if the flux is, so we need the speed, if the flux is 60 milliwebers. All right. So given a flux of 60 milliwebers, the question is determine the speed. That is our question. We need the speed. Okay. So this is what we are going to have, having our speed according to the formula that we are given. It's already having a 60. So meaning to say the speed will be in revolutions per minute. Unless you want to change that, you remove that 60, you calculate the speed in rests per second. It's up to you. So from the formula that you are given, you are going to substitute the values, or you are going to make what you need to be the subject of the formula. That's how you can answer this question. What is it that you need? It is the speed. So you can make the speed the subject. Remember, from your mathematics N3, you worked with this change of subject. All right, so cross multiply, that is, we are going to have 60C times E. Then 1 multiplies this side, or actually I could have just multiplied this one by 1. 1 times this side, so it's going to be 2 flux. NPZ is equal to this 60C multiplies the E, so it's going to be 60C E. All right, what we need is the speed. Remember, what you need is the speed. So you're going to divide by the 2, the flux, the P, and the Z to remain with the speed this side. Okay, so that means this part here, we are going to divide by 2, which is what we do not need here, by the flux, by the pair poles, and the number of conductors. So that is, we've got our N as the subject. Having the 60 here, it means this speed is in revolutions per minute, revs per minute. So this N that we are going to calculate, it is going to be in revs per minute. Answer that you're going to obtain automatically, it is revs per minute. So it is just substituting the values that you are already given. In this case, we've got our values, the pair poles, and so on. So you can substitute this. So our speed, that is 60 times C, which is for a wave, that is 2. Then E, which is the generated EMF, remember that is 400. Then we divide to 2 times the flux, that is 60 times 10 to the exponent of -3. The pair poles, they are 4. Then also the number of conductors is direct 118. So this is how it can be. So by substituting these values on your calculator direct, this was going to give us a speed of 847,458 revs per minute. That is the idea there. So these are the typical questions that you might be given where you just need to manipulate the formula that you're given, change of subject, then you can substitute your values onto the formula that you're given, or you can even just substitute direct on the formula that you are given. It's up to you, or you can make the subject. So these are the typical questions that you might be given. So I need us to work as much questions as we can. So let's see this one, question number 3. A 4-pole DC generator armature. So that's, okay, so let's just take our information in this case. So it's a 4-pole. How many pairs are we having? 4 divided by 2. That means we've got 2 pairs. Okay. Then we are given it is lap wound. Lap, for a lap, we know that C is equal to 2P. So that is, if we are to multiply this 2 times 2, because remember our pair poles, that is 2. So 2 times 2 is going to be a 4. So let's see what you're given. So you're given that in this case, with the 60 coils, each coil has got 8 turns in this case for each coil that you're given. So take note, we have given 60 coils and it has got 8 turns. So meaning to say we are going to obtain the number of conductors from there, which is our Z. So the number of conductors, how are we going to determine, or how are we going to have these number of conductors? So in this case, we are going to multiply number of coils to the turns that you are given, which is 60 times 8. So this now, because consider that remember we are dealing with a lap. So we are going to also consider for a lap multiply by 2. So this means we are going to have 960 conductors at the end. So that is going to be 960 conductors at the end. Okay, so we've got 960 conductors. Determine the flux per pole required to generate 200 volts at. So you're given the generated EMF, which has 200 volts at this speed. And our speed is in revolutions per minute, revs per minute, which is 1000 revs per minute. So what we need is the flux per pole. So what is the flux per pole? So as we can see, it's just the similar part as the previous question that we had, where we just need to make flux, the useful flux, the subject of the subject of the formula from what we are given. So this is our flux. So again, this is same as over 1. You cross multiply. So that means we're going to have 2 times the flux, speed, the pair poles, which is equal to 60 CE. What you need this time is this flux. So meaning to say we're going to divide by 2 and this rest of the other part of your equation to remain with the flux. So that means our flux is going to be given as what? So this is going to be 60 CA like this. All right, so you're going to divide by 2. So we have to divide by this 2. Speed, the pair poles, and our conductors. All right. So that is the idea there. So depending with the condition, but if you check mostly working with the flux, you're going to see that your answers, they are to milliwebers if you're working with the flux. So to convert to the milliwebers, remember, milliwebers, that is times 10 to the exponent of -3. So to convert to these milliwebers, you multiply by the opposite, remember, which is times 10 to the exponent of 3. This is to convert your answer to milliwebers. So meaning to say automatically the answer that you are going to have will be in milliwebers. So let us substitute what we are given in order for us to determine our useful flux. So that is 60 times C. Remember, our C was a 4. Okay, this is a lap, so that's going to multiply. So that's a 4 times E. We generated EMF, that is 200. So you're going to have 200. You divide. All right, so you're going to divide to 2 times the speed. Okay, let's see our speed, 1,500. 1,500, the pair poles. Remember, our pair poles is 2. Okay, so you're going to have 2 pair poles. The number of conductors, how many conductors? 960, that's our Z. 960. So like I said, by multiplying this by 10 to the exponent of 3 is converting our answer direct to milliwebers. So meaning to say, whatever that you're going to have on your answer, automatically that will be in milliwebers. So the moment you multiply this, you're going to have something like 8,333 milliwebers. So that is our useful flux. So these are the typical questions that you might be given where you need to apply the conditions of the questions, like how the question is given, the information. All right, number 4, we are given a DC. We are also having a DC generator there. It has an armature of EMF, armature EMF of 100 volts there. So we're given the armature EMF. All right, so let's see. That is 100 volts. When the flux per pole, so you're given also the flux per pole to be 20 milliwebers. And the armature speed being 800. So we're given the speed 800 revs per minute. Okay. Calculate the EMF. So guys, look here. We already have the EMF, but they're saying calculate the EMF. Why? If you check 4.1 with the same flux, but the armature speed off. So this now is the type of question that we discussed here where the conditions have changed. So using this condition where the speed can remain the same or it can change, it means these are your initial conditions. So it is because of the question that we are having, it is the one that tells us. So these are the initial conditions where we are going to present this as E1, flux 1, N1 at the initial conditions. But now later on, the question is we are supposed to calculate the EMF, meaning to say we are supposed to calculate E2 with the same flux, meaning to say the flux has not changed. Flux 2 is equal to flux 1, which is 20 milliwebers. It has not changed. But the armature speed of the speed has changed. At this condition, our speed is now at 1000 revs per minute. So that is the first part of 4.1. So what is going to be our E2? So if you had to check from the formula that we had, we said E1 over E2, it was supposed to be a constant, but those constants are cancelled. So at the end, we are just going to remain with N1 flux 1 like this over N2 flux 2. But on a consideration that flux 1 and flux 2 are the same. These two are the same, guys. They can just cancel also. You can substitute your values, it's fine, but these two, they're the same. So there's no need for us to substitute these because it's the same thing. This part and this part, you're told that it's the same. So remember your E1 is 100 over E2, which is the one that you need to calculate. It is equal to N1, which is 800 over N2, which is 1000. Remember the flux 1 and the flux 2, say they are the same. So there's no need for us to consider that. So we can cross multiply. That means by cross multiplying E2 times 800, that is 800 E2, which is equal to 100 times 1000, that will be 100,000. So we can divide by 800, guys, both sides to determine our E2, which is the generated EMF at this condition that we are given. So that was going to be 125 volts. So that is how you can attempt this typical question. All you just need is to make sure that you apply exactly according to the information that you are given. So that was 4.1. So 4.1 is a condition on its own, which is taken from the initial condition, but you refer that part as your final consideration. 4.2 is another part again on its own. So we have to consider what is it that we are given on 4.2. So on 4.2, from these initial conditions, we are given to calculate again the generated EMF. What we need is to calculate the EMF. But this time, the flux is 24 milliwebers, meaning to say it is no longer the same as what we had previously. And the armature speed being 900, the speed is not even the same as what we are given in the previous sec, because the initial condition, the speed is at 800, but this one, they're saying the speed is 900 revolutions per minute. This is the second condition. There is nothing that is the same from the initial condition. We do not have anything which remained the same. So still our formula does not change. The constant, it is the only thing that we know that the constant will cancel. So meaning to say the N1 flux 1, this time there's nothing that we are going to cancel because these flux that we are having, they're different, the speed different. What is it that you need? Let's substitute, all right? So you're given E1, which is 100 over E2, which is the one that we need is equal to N1, which is 800 times the flux, which is 20 milliwebers. Since this is also in milliwebers, there is no need for us to write that. Yes, you can write, guys, times 10 to the power of minus 3, but there's no need for us to write that, okay? Then the speed being 900 times the flux 2, which is 24 times 10 to the power minus 3. So like I said, there's no need for you to write these times 10 to the power because the units are the same. There's no need for us to write this. This will cancel. The units are the same. So there is no need at the end. All right. So if you can also just reduce, if you are someone who can just even reduce the values that you are given, that is 100 over E2 is equal. Just try to reduce this, multiply on your calculator, 800 times this over 900 times 24, it is going to be 20 over 27. At least you can work with a reduced value, then you can just cross multiply. I'm not saying using original values that you're given, that is wrong. You can use those values, but you can even, guys, it's a calculator, this one. You can reduce E2 times 20, that is 20 E2, and the product of the 27 and the 100 is going to be 2,700. So we divide by 20 both sides to determine E2. That is the condition. And that was going to be 135 volts. So these are the typical questions that you might be given. All you just need is to work on more questions, more consideration, like how do they ask these questions in your typical exam. But all is on this part. Know your formula, the conditions that you're given on your formula, and also when the conditions have changed. Like initially you were given a certain condition, then the second part, you're now given where the flux or the speed is changing. This is the best part that you are going to use, which is simply taken from the relationship that is between the generated EMF and the speed and the flux. So more to come from Maison African Motives till we meet again.